Hi everybody, and in this video what we would like to do is show you some further Python techniques for, in this case, solving differential equations numerically. Okay, so I'm going to demonstrate this technique, two techniques, using systems that already have analytical solutions that will allow us to compare our numerical solution with the known analytic solution and show that the algorithms are valid, that they're valuable. So this way, if you apply these to a system that either doesn't have a known solution, or at least that you don't know what the solution is, as long as you apply the method appropriately, you will be able to have some confidence that your results are the actual solution to your problem, or at least a reasonable approximation. Okay, so we're going to start with free fall, and in terms of the velocity equation, if I launch an object upward with an initial velocity v naught, then its velocity at any given point in time is given by this equation. V equals negative g times t, where t is our time parameter, g is the gravitational acceleration of Earth, and v naught is our initial velocity that we're launching the object with. And if I want to solve this equation for the displacement or the position, then this becomes a first-order differential equation. Now, this is a trivial process because the acceleration here is constant, and if you consult any introductory physics textbook, they will give you a host of equations that allow you to compute the trajectory of an object where the acceleration is constant. But this is a simple system with a known analytic solution, and as a result, it is a good system to demonstrate this technique with. And by the way, okay, this technique is called the Euler method, right? And so what the technique hinges on is looking at your differential equation as a difference equation. And I'll explain what that means here in a moment. But if I were to treat this as a genuine differential equation, then the simplest approach to solving this analytically would be separation of variables. On the right-hand side, your only variable is t, and your integration variable dt is on the denominator of the derivative. And so we can just move dt up to the right-hand side, and we can integrate. And when I do that, I get negative 1/2 gt squared plus v naught t plus x initial, or x naught, and x naught is my integration constant, and in this case it represents the initial position. So in our example here, we're going to assume that the initial position, or x naught, is 0, and this means that we're launching our projectile from the ground. Okay, and we're giving it an initial boost of 20 meters per second. And with these values in mind, and given how we have set the velocity equation up in the first place, this is assumed to be a coordinate system where up is positive, right? So just make a note of that, and that's why we have a positive value on v naught and a negative sign in front of g. So this analytic result is what we're going to input into our computer model, and we'll actually compare the results of the Euler method with the analytic solution. Okay, so how do we think about this computationally? If I want to do a numerical solution to this, what do I need to do? Well, what we do is we replace our dx with the difference between some final point xf and some initial point xi. Now, these are going to be two successive points, okay? This xf and this xi are going to be two successive points, and I'm going to move the dt in the denominator to a delta t. And in principle, you could take delta t and write it out explicitly as tf minus ti. But as you'll see in the computation, it's actually easier just to leave it in this kind of form, delta t or dt or whatever. And remember that it just represents the time interval at which you're going to measure each successive point in space, or your x values. And notice I haven't done anything to the right-hand side except I've given a subscript on the t. And actually, as a matter of fact, I need to put a subscript here. Okay. And I'll explain what this I means here in just a moment. But so far, all I've done is solve for xf, right? And this is the equation we're going to program into the computer. Negative g times ti plus v naught, all of that quantity times my time interval plus my initial position. This is the estimate of my final position after a given time step. And once again, we'll see what this means. But projectiles come back and they hit the ground, and we need to have some sense of how long to run our simulation to keep it physical. And so we compute the total time of flight, which turns out to be about 4.08 seconds. It's, in fact, just slightly more than that, but just taking it out to 2 decimal places, 4.08 seconds. So this is the total time that we're going to use in the simulation. So let's actually pull up the code. And once again, we're using Python Baba. And here I've imported NumPy as MP. And I've imported matplotlib.pyplot as PLT. So these are the numerical and plotting packages that we'll use. And here I'm defining the variable g to be 9.8, the acceleration due to gravity. My initial speed v naught is 20, and if I want to be very specific, this is in meters per second, and gravity is in meters per second squared. And my time, the array for my time, is going to go from 0 to 4.8, and I'm going to use an interval of 0.08. So this is going to give me 51 individual data points at which to try and compute the trajectory of the projectile. And my dt, or the time increment, this was from an earlier trial, the time increment is going to be the second element in the t array minus the first element in the t array. And if the increment is 0.08, then dt should equal 0.08. Okay? And I'm also creating an x array to hold my x values, the ones that I'm going to compute. And I'm creating an empty, well, actually it's technically not empty, it's full of zeros. An array of zeros with the same length as my time, so that way my time and my x value, or my time array and my x array have the same number of elements, and therefore can be plotted against each other. Okay. And here we actually have the whole loop. Okay, this is where we're actually computing things. So I'm going to come back here. I'm going to talk about this equation. The f here in this equation does not mean my final position completely. What we're doing, what this algorithm is going to do, is you give it two inputs. I have to know the initial velocity, which we've set to 20, and my initial position, which I have set to 0. And what this is going to do is I'm going to say, let this be 0, and let this be 20, and let this be my first time. I then compute this number using 9.8 times 0 plus 20 times 0.08 plus 0, and that will update my next value in my position array. And then this position becomes the input xi for the next position in the array. And I would then use the next time value in the array as well. So remember that Python indexes from 0. So initially, my the very first run through this, my final position is going to use the t0 element for my time and the x0 element for my position. And that will compute x1, or the x1 element. Then this becomes the x1 element, and this becomes the time 1 element, and that allows me to compute the x2 element. Okay. So if I come back to the code, what we'll see is that the way I've arranged this loop is that because my first, or I should say my initial conditions are already set, I want my x initial element and my t initial element to be both 0, then I don't need to compute this loop the total number of array times, or the total number of elements in the array. Since the first elements in the arrays are already computed, I need to compute this loop one less time than that. So that's why I have the number of times to compute the loop as the length of the time element, or 51, minus 1. So I only need to compute this actually 50 times since the first elements are already supplied for us. So what this is saying is, if I equals 0, then this element is going to be the x1 element. This is going to be the t0 element, and this is going to be the x0 element, and we use those two elements to find the next x. Then, once it's done, the I is going to move to 1, and I'm going to compute the x2 element, and this will be using the t1 element as supplied from the array up here. And this will be the x1 element that we just found, and we just keep doing this over and over and over until the loop runs out. Here is the analytic solution that we found from calculus, and here we're plotting the numerical solution. And so I'm going to plot t on the x-axis and my positions on the y-axis, and I'm going to plot these with black circles. And then we're also plotting the t and analytical solution in red lines, and then we're going to show. Now, these last two lines are just a matter of taste for me, okay? And they're going to be instructive. So this first print statement okay, is telling you to print the difference between the numerical solution and the analytical solution at the first element. So after we run through this loop the first time, what is the difference between x1 and my analytical solution, its first element? Okay, because these should be, in a perfect world, these would be, this difference would be 0, because these elements would be the same. Then, what we're asking the program to do is take the very last elements in the array, in both arrays, my numerical solution and my analytical solution. I'm finding the last elements, and so remember the length of the T element, or the T array rather, is 51 elements, but because Python indexes from 0, the index on the X elements will run from 0 to 50, giving a total of 51. So the 50th index will be the last one, so I need to take 51 minus 1, and that will give me an X index of 50. Same thing with the analytical solution, xan. And what this will do is will allow me to evaluate the two solutions, the numerical solution and the analytical solution. Ideally, they should be as close as possible. Okay, so let's run the algorithm. Oh, and the last line just ensures that my time and my positions have the same number of elements. Now, this is trivial because this line of code wouldn't work if that weren't true. Okay, but this actually allows you to see what the number of elements are if you're curious. If you don't want to divide this interval by your increment in your head, then you can just have the program print the number of elements. So let's run this and see what we get. Okay, so this first number, print the difference between my numerical solution, its first element, and the first element in the analytical solution is 0.03. So this is your index of 0 point. This is x1 and x analytical 1. And you can see that they're about 3.1 centimeters off, which is not bad. But there's a noticeable deviation as we go through the simulation, right? As we increase in time, we lose accuracy. The black dots don't quite line up with the white dot, or with the red line. Okay? This is an artifact of the Euler method. Now, the Euler method is the simplest method with which to solve first-order differential equations, but there is a cost, and that cost is to get really good viable solutions, you have to take your time intervals to be fairly short relative to the total amount of time that you are simulating. So in fact, 51 data points is just not a lot. So what this is basically doing is that there's rounding error in all of the individual measurements, and the rounding error is getting compounded because if each individual measurement would contribute in principle the same amount of error, then as you introduce more and more error into your position measurements, each individual data point is contributing the same amount of error to it, so that error is just growing and growing and growing, and eventually your solutions diverge very noticeably. So the main limitation with the Euler method is you have to choose not coefficients, but time increments that are sufficiently small to obtain whatever accuracy you desire. So what will happen if I change this to 0.01, right? What will happen if we change this to 0.01? Oh, that's a lot better. Okay, so the main point with the Euler method is smaller time increments are better. However, there are also limits to that. Okay, I'm not going to go into the details of truncation and those types of issues, but your best accuracy is going to be achieved at some increment in time, and if you go less than that, you'll actually start to lose accuracy again. So there is a sweet spot. We're not going to go into all that. For our purposes, we're just going to say trial and error, and you'll notice, by the way, actually if I change this back to 0.08, let's run this one more time. You'll note by the end, the very last element, my solution is off by 1.567999 meters, or effectively 1.568 meters. Okay, so on this scale, there's about 1.5 meters between my black dot and the red line in the vertical position. Okay, so about 1.56 meters. When I change this down to 0.01, you'll notice this goes down to the centimeter range. There's only 19 centimeters, almost 20 centimeters difference between these two. The red line and the black dot down there. If I go even further, 0.5. If I go even further, then I start to get very good precision, right? And usually at this point, for a lot of purposes, this would be sufficient, right? We're down into the centimeter range for the deviation at the end, and the black line and the red, or the black dots and the red line are lining up just fine. Okay, so for an elementary application, this would probably be good enough. You could definitely play with this and see what happens. Python is relatively fast, so even if you're using the online version, it should execute a lot of your code relatively quickly without too much problem. And if we go down to 10,000ths of a second, then we obtain less than 1 centimeter in precision, or accuracy rather, with our last data point, which that's really good. So basically the Euler method is a very powerful tool for solving first order differential equations, provided you give it the appropriate type of increment in time. Okay, but and notice, right, if my time increment is 1/10,000th of a second and I'm going for 4.08 seconds, then I have 40,800 data points in my plot here. Okay, so all of that is well and good. If you have a first order differential equation, just choose your time intervals to be appropriate, and you will get increased precision. And this shouldn't be too much of a surprise, right? Because derivatives and integrals relate instantaneous quantities. So the larger you take your time interval, the less information you are capturing in between the 2 points you're considering. And so the wider and longer you make those 2 points, the less valid the approximation between those 2 points is. And as a result, the errors in your calculations will just grow and grow and grow and grow and grow. And that is why when we saw at 0.08 seconds, there was that noticeable deviation between the line and the black dots. All right. So how does the Euler method do with a second order differential equation. So consider a mass spring system. I have Hooke's law, and writing my force ma as the second spatial derivative with respect to time, or the second position derivative with respect to time, and dividing both sides by the mass, then I'm going to get my second derivative in time, or second derivative in position with respect to time, is equal to negative k over m, which represents the square of your angular velocity, times my position. So what we want to do to make this as advantageous as possible is to convert this into two first-order equations. So we can do this because it turns out, of course, that acceleration is the derivative of velocity with respect to time. So instead of setting my second-order derivative, I can just set the first-order derivative of velocity equal to my Hooke's law force, negative k over m times x, and then use the definition of velocity that my derivative of my displacement is equal to the velocity. So now I've reduced a second order differential equation down to a first order. And generally when you're working with Newton's laws, you're working with accelerations and velocities and so on, anytime you have a second order differential equation, you will almost always be able to reduce it in a form like this. So now we're going to convert these two equations to difference equations. I'm going to take Vf minus Vi over my time interval is equal to negative k over m times xi, and xf minus xi over my time interval is equal to Vi. Solving for my final quantities in both cases, I get this set of equations. So this is what we're going to program into Python. And I'm going to let k have a representative value of 25 newtons per meter. And I'm going to put 0.25 kilograms of mass on my spring respectively. Now, once again, to know about how long to let the simulation run, I need to have some sense of how this system is moving. So I'm going to compute the period of oscillation, and the period of oscillation is about 0.628 seconds. Okay, so even though 6 seconds is not an even multiple of that, it'll allow us to capture several cycles, and that will allow us to evaluate our model fairly simply. Okay. Now, once again, these f's in the equations are not final quantities of the entire motion. They're the final quantities after each individual step of the process, right? So we start with initial conditions, and I'm going to start with an initial condition that my position on the spring is negative 10 centimeters or negative 0.1 meters, and that we're starting our velocity from rest. So this is the situation where you pull a spring down, you're holding it, and then you release it from rest and see what happens. So our F's represent the final point in each step. The I's represent the initial points in each step. Delta T is just the time interval between two successive times in the calculation. And K over M is the square root of the angular frequency. So my code, once again, I'm importing numpy as np and importing matplotlib.pyplot as plt. I'm defining my constants k and m. Now, I haven't commented through on this code. But we can see what's happening, right? So we said that we're going to go from 0 to 6 seconds for our time interval, and I'm choosing a time interval of each successive element in the time array to be 0.01 seconds. And the my delta t, or my time interval, is going to be the first time element minus the 0th time element. But now I have to define two arrays in x and z. Since this is second order, I need to compute both of those to compute the next set of both of those. I can't compute velocities without positions, and I can't compute positions without velocities. Okay? Why can't I compute my velocities without my positions? Well, my velocity at each next point depends on the previous position, okay, as well as the previous velocity. And as written, if we come back here, okay, you'll notice that my final position is going to be my initial position times time, my initial velocity times time plus my initial position. But here I'm computing the final velocity over a time step, okay? But as written, Euler's equations would look like this, okay? And so here's the loop. Oh, by the way, here's the initial condition for my position. And since I'm letting my mass start from rest, then its initial velocity will be 0, which is what it's set to anyway, so I don't need to explicitly define that. But here is the bulk of the program. Here's the algorithm. I've got my velocity at each next time step to be computed by negative k over m times the position at each time step times dt, or my time increment, plus my velocity at each time step. And then I'm going to compute my next position using my previous velocities and previous positions and my time increment. Okay, this is the analytical solution. We know Hooke's law gives us oscillations, and my amplitude, if I release my object from rest, then that will be my amplitude. So my amplitude is going to be 10 centimeters. I initially allowed it to be pulled down to an initial point of negative 10 centimeters, or negative 0.1. So what that means is, because it's starting at a maximum amplitude, this is going to be a cosine function, and it will be cosine times the square root of k over m times my time, but also plus np dot pi. So this is my phase constant, and this comes into play because I'm releasing the object from the negative x-axis. Okay? So I need to put the phase angle into my analytic solution, right? And then I'm plotting the numerical solution, the results of this loop, the times and positions. So my times are going to come from my A range array, and my x's are going to come from the results of this loop. And I'm going to plot the times and my analytical solution once again. Now we know that this is going to be oscillatory, right? We know this is going to be oscillatory. So let's run the code. Okay, so the red lines are the the analytic solution. This is what we expect the system to do. And you'll notice that very quickly the Euler method produces a very divergent solution away from the actual analytic solution. There are a multitude of ways to get around this problem, but the root is that the Euler method is simply not convergent for a second order system. Those individual errors that are creeping in now creep in at a much faster rate, because that's just the nature of second order systems. Okay. So how do we fix this? Well, one of the cheapest ways to fix this without inventing or programming a brand new algorithm. Now, there are more powerful algorithms than what I'm about to show you, but for quick and dirty, and for just at least getting a sense of what's happening and also achieving a reasonable amount of accuracy, there's one very quick fix. And that is, instead of using your previous velocity to calculate your updated position, use the velocity that you just calculated in the previous step. This simple modification of using your updated velocity to update your position, this is called the Euler-Cromer method. Okay. So this is the Euler-Cromer method, and this is just a very powerful and quite elegant and simple fix to an otherwise untractable problem. At the very least, we would not be using the Euler method to solve double order systems, okay, or second order systems. So what do we get when we make that correction? Now notice, by the way, your oscillation period is dead on, right? I get a maximum here and a maximum here, maximum here and maximum here, maximum here and maximum here, and so on. And so I'm not worried about the phase shift right to the right or the left of my graph. I'm just worried about how wide the disparity is, and I'm claiming that doing that little trick will fix things. Sure enough, now look at the agreement. That is quite stunning, really, right? If you absolutely wanted to, you could put in a similar line of code that we had in the other program. So let's see what this does. Yeah, right. So I'm off this last data point. I'm only off by well, I'm going to have to think that through. I'm going to have to think through what it's telling me. But the point here is that this is a very, very good match, right? Very good match. And so it's quite easy to see that that little tiny correction does a really good job of fixing how disparate the original Euler-Cromer method was when applied to systems beyond first order. Now, there are many more sophisticated algorithms, but they all require some pretty advanced, or at least time-consuming coding, right? So this is a very quick and dirty way to get a relatively good answer. And a very useful answer, very helpful answer, right? Oh. I forgot to put the minus sign. I want to know what the difference between these two is. That's what these two numbers are. These are just the physical actual positions. This is the position of the analytic solution. This is the position of the numerical solution. I want to take the difference between these. And let's see if this works. Yeah, so my analytic solution is larger by 1.7 millimeters, right? So these are off by orders of magnitude less than the maximum values that you achieve, right? Your maximum values should be 0.1, and 0.0017 is over 500 times that small. So you've got a couple of orders of magnitude between how big your results are, or how big your amplitude is, versus the error between the two measurements. And so that's quite good. That's quite stunning. And we're capturing several cycles so we can convince ourselves that our analytic solution and our numerical solution do indeed match. Okay? So, I hope that this particular procedure might prove helpful to you and for you. And with that, I'm going to sign off and say that we will see you in the next video.